right, shall we get started? Everybody ready? So first of all, I think that the fluids are due today, right? Over by noon today, right? So I hope that went well. Yeah, we are almost done grading the Jello thing. Sorry that it took taking so long. I want to make sure that there's quite a few of you, so I want to make sure that the same standards are applied to everybody, so it's fair. Not like one TA thinks this is less important than like the other one, and so on. I guess you still cannot see the results, right? We haven't published them yet. So okay, so hopefully soon. We need to, yeah, some of them are already in, but I think we just need to publish them when they are all in. Somehow, that's how Canvas works. Yeah, I think by now everybody submitted the final project description, right? It's quite a few. Some people didn't do it like last minute, but I hope everything is now in. So funny thing happened. Turned out that some topics ended up being more popular than others. Like position-based fluids, I think we have now 3 groups doing that, and I sort of allowed that because I thought it will be sort of interesting to see how 3 different groups of people will approach the same topic. Interestingly, in this case, we have like 1, 2, and 3 people. So I guess the really important message is that if there is a project with 3 people, then I expect you to do more than a project with 1 person, right? So basically, what you do is going to be weighted by the number of people. So it would be funny if like the 1-person team did a better project than the 3-person team. I guess the main point is that you need to explain what you have actually done. You don't have to say who did what. It's like you work as a team, but I would expect bigger teams to get done bigger things. And there is always infinite amount of work on any single project, right? You can always like do creative things with like the rendering or reconstructing surfaces and whatnot. All right, so do you have any questions on the projects or homeworks or something? If not, then we will continue with our finite element method, which I started the last time. We are following this SIGGRAPH 2012 course note by FTHS. And we will just finish it today. This is also the precursor for the projective dynamics paper, our very recent SIGGRAPH paper. Some of you, actually I think at least 2 groups also chose to implement that, which is gonna be cool. And this is what it essentially builds on top of. That's why I put this here earlier. Okay, so let me quickly recap where did we leave things off the last time. So I discussed how to create a thing called deformation gradient, which is a 3x3 matrix conventionally denoted as F, and this is a deformation gradient. So we are assuming we are in 3D. You could do the same thing in 2D, but usually you need it in 3D. What was the deformation gradient? Can somebody remind me? I guess I discouraged everybody for shouting at the class when I said that piazza also counts. It takes more courage to stand up in the class. I never have discouraged myself. A deformation gradient is easy. What you do is you just take a rest pose tetrahedron, right, which gets mapped to some deformed tetrahedron, whatever. And the deformation gradient essentially is the linear part of this mapping, right? There's the affine part, the translational part, and the linear part, the actual deformation of that thing. That's what's captured by the deformation gradient. So that's what we derived the actual formula for the deformation gradient the last time. Remember, by looking at these edges of one tetrahedron, edges of the other tetrahedron, from this you just solve a simple matrix equality and find the deformation gradient. Now everything else depends on the deformation gradient. A particularly important quantity is the notation is not great, but let's just call it EI, the elastic energy due to the tetrahedron number I. So let's say this is a tetrahedron number I. And the elastic energy would be this. So what is the WI? That's the volume of Ti. So Ti is my tetrahedron. And this means the rest pose volume of the tetrahedron, the Wi. So I'm looking at this one. So I always have some sort of notion of a rest pose. That's where the material is started with. That's where the material is undeformed. And I have some current configuration, right? You have seen this many times before. Now, what is the psi I thingy? What is it? Does somebody remember? Oh, by the way, last time funny thing happened when I was recording the video. I just like stopped like 10 minutes before the end, so I had to merge the video clips. Not sure if you have looked at this, but I guess it would work. You just put them together. I guess not many people watched 10. So the psi I is the elastic energy density, or deformation energy density. Yeah, that's the nice term for it. And essentially energy density function. And the psi I is a function from the deformation gradient, a 3x3 matrix, which assigns it a non-negative scalar. And this Fi is the deformation gradient for tetrahedron Ti. So I guess I could give it an I here too, right? Why do I bother about this I? The I indexes tetrahedra, and the thing is that every single tetrahedron can have a different deformation gradient, obviously may have a different volume, and may have different material properties, so can have a different energy density function. That's why I put here these I's. Okay? Oh yeah, why this multiplication is essentially what remained after I said that we are using just linear shape functions, because before there was the fully general formula was integrating this, right, the psi I Fi over the volume of the undeformed tetrahedron like this. But if the deformation gradient is, if the deformation field is linear, then the deformation gradient is constant. So this also, of course, becomes constant. So this whole integral reduces just to multiplication by the volume. Right. The practical significance of multiplying by the volume means that you don't have to worry about having big elements next to small elements, right? You can have something like smaller elements and even smaller elements and completely tiny elements over there, right? So clearly the small elements should contribute less to the energy, right? And that's what this takes care of. So that's sort of nice. If you remember when you had to tweak the weights for mass spring systems, that's not so easy. Here it gets a little bit easier because at least these effects are taken into account for you by the finite element method. Now let me put their numbers so I know which paper is which. Okay, and the last time I discussed what are the good models for this energy density function, and we came up with one that was sort of nice. So good model for, oops. What was the nice model? It was this. So let me drop the I. Let's just work with one tetrahedron, and you will remember that you can do the same thing for different for all tetrahedron. Each of them can have different parameters. So the good model which we came up with after lots of failed attempts was this one. Which is equivalent to F minus R F squared. Remember what is the sigma? That's the matrix of singular values after taking the SVD of F. So I guess I could, just to remind you, I could do this, right? Then this R is also a 3x3 matrix, and that's the best fit rotation. So the R is UVT. And the one thing you need to be careful there, that's what I think I successfully confused you with the last time, you need to be careful that in the SVD, the U and V need to be proper rotations, meaning that the U and V need to be from SO3. Usually SVD only guarantees that U and V are from O3, meaning that they are orthonormal, but that means they can include reflections, right? We need to, if we want to be real, if we want to capture realistic material, no realistic material can really reflect, right? Reflection is sort of like an artifact of simulations, right? Like imagine like piece of rubber or something, it cannot even compress to zero volume, right? Let alone to negative volume. So this reflection is something that happens only in simulations, right? And certainly you want to prevent it, or if you cannot prevent it, because sometimes you just can't, sometimes it just happens, you can't weasel out of it, then at least you want to define your energy which generates forces which wants it to push back to the correct state. And for that to work, you need to make sure that the U's and V's, and consequently this R, is indeed from SO3, which means that it's orthonormal and the determinant is +1. And how to do that for SVD, which does not have this property, which only gives you orthonormal matrices, that's what I was trying to explain the last time. The trick basically is to invert the last single value here and flip the last column either of U or V. Okay? Is that clear? Do you want me to explain that again? Or, well, you can also go back to the last video. Well, tell me. So I will take it as it's clear. Because we have lots of other things to explain. So one interesting thing, and this is new, this is what I did not mention the last time. One interesting thing you can notice about this model, if you look at just sigma minus I, how many degrees of freedom is in sigma? Or let me start with F. How many degrees of freedom has F, the deformation gradient? That's easy. It's a 3x3 matrix. So it has obviously 9 degrees of freedom, right? So how many degrees of freedom is in sigma? Come on, don't be shy. You know it, yeah? 3 degrees of freedom, right. So this material model I presented here, which is close, not quite there, but close to correlated linear elasticity, which is one of the most popular materials used in computer graphics and physics-based animation. And I will get to that in a little bit. How do you get to full correlated elasticity? But let me first explain this. The sigma has only 3 degrees of freedom, right? So from the 9 degrees of freedom originally present in F, somewhere we lost 6 of them, right? Because now it depends only on the three which are in sigma, right? Because this is the formula, so it only has 3 degrees of freedom out of the total of 9. So the natural question is, like, are we losing something? What happened? Like, where did the 6 degrees of freedom go? So you should know where 3 of them went, and now I will tell you where the other 3 went. So the answer is we are not losing anything if we assume, and watch what we assume isotropic and rotation invariant material. So what meant the rotation invariant thing? That's what we discussed the last time. That's actually why we arrived to this formula at the first place, right? Rotation invariance wanted this. Wanted RF to be equal to psi of F for every rotation R. Now this R, there's like a thick line, so this R is a different R from here. I hope that doesn't confuse you. And that simply means that if I have a blob of elastic material, if I rotate it somewhere else, the energy must be the same, right? That's the same for Mass-Planck system. That's the same for any reasonable model. So this we always want, right? Isotropy is something we may not always want, but it turns out that most practical materials are isotropic. What means for a material to be isotropic? You must know that. Most of correct. There is no preference. All directions are equal in the material space, right? So there are, of course, you can probably easily come up with materials which are not isotropic, right? That would be example of like non-isotropic material. Be creative. You mean like cloth? Yeah. That could be like even more extreme cases. Like imagine if you want to do a 3D example, imagine you have like a steel reinforced concrete, right? If you have like a concrete slab and you have steel rods in this direction, right? Now obviously the steel rods will produce lots of stiffness in their direction, but maybe they would bend relatively easily compared to how difficult it would be to compress them, right? So that would be an isotropic material. Nevertheless, usually for most cases in physics-based animation, you will be dealing with isotropic materials, sort of makes sense that there is no preferential direction. I think wood would be another example, right, of an isotropic thing. If you have like a tree growing in one direction, there's obvious one preferential direction. So what means, how can we express isotropy mathematically? So isotropic, what does it mean? There is a very elegant condition for a material to be isotropic. So my psi is isotropic if and only if this is true for each r rotation. So what is the difference from this? Here I am multiplying with r from the right. Here I was multiplying with r from the left. Looks like a very subtle difference, but it actually makes all the difference between rotation invariance and isotropy. Because let's think about it for a second. What does it mean? If we are multiplying from the left, that means, you know, the vectors, the things you are transforming, they always go from the right, right? So it means you first apply the deformation gradient, so you go to the deformed space, and then you apply the rotation, right? That really means that you are taking the whole thing and just rotating it. Now, what does it mean here? Here it means that you first rotate in the material space and then apply your deformation, right? So this says that it does not matter how you rotate in the material space. If you have some small blob of material, whatever way I turn it, the energy is going to be the same. So in a sense, this is invariance to change of coordinates in the material space, and this is invariance to change of coordinates in the world space. In the world space, it means invariance to global rotation, and in the material space, it means isotropy. That means that the material behaves no matter how you locally orient it. Behaves the same no matter how you locally orient it. Okay? And if we have these two assumptions, if you have a material which is both isotropic and rotation invariant, well, then if you take the psi of f, for any f I can write SVD, right? So I can write u sigma vt, where u and v are rotations. And because I have both these properties, well, then it must be the psi of just sigma, right? So it turns out that if my material is isotropic and rotation invariant, I'm really not losing anything. Or where the 6 degrees of freedom went, 3 of them went to rotation invariant and the other 3 went to isotropy, where essentially consumed. That basically you can also look at it as symmetries in the material model in the psi. Okay? So that was a rant about isotropy. And now I owe you the explanation what is still missing from this material model. This sort of looks like a nice material model, right? But there is something missing there. So what is missing there? What is missing there is volume preservation term. So let me explain that here. So let's assume I have this small block of material, just like a little square. Imagine that's like a small blob of material. And I have one deformation that deforms it like this. So I will draw the reference square here. And imagine that one deformation squishes the square like this. And then I have another one that does this. So here is the reference one. That's the undeformed chunk of material. And let's say this one extends it a little bit. So that does this. So this would be, let me call this one F1, and this will be called F2. So the F1 deformation field is this. XY will be 3/2 x and 1/2 y. And the F2 would be, what would that be? Well, it would be 3/2 x and 1.5 y, right? So the idea is here I stretch the, so of course this is the x-axis, this is the y-axis, right? So here I expand the x-axis by 50% and compress the y by 50%. And here I extend both the x and y directions by 50%, right? So what does it mean for the deformation gradient? What deformation gradient this thing has? Well, it's just 1.5, 0, 0, 0.5, right? This is such a simple deformation. Same thing here. This is a linear deformation, so the deformation gradient is trivially differentiating this. So this is 1.5, 0, 0, and 1.5, right? This is just 3/2 is 1.5. So those are the deformation gradients of these two deformation fields. So if I do SVD of these matrices, what do I get? Well, these matrices already are in the SVD form, right? The rotations are just identities. These already are diagonal with non-negative entries on the diagonal. So this already is the sigma 1, and this already is the sigma 2, right? So if I use my material, if I do this, the sigma 1 minus identity, so I'm looking at my, let me just remind you that. So that was, the material model was k-half. Let's just say that the k is 2, whatever. And that's sigma minus identity, Frobenius norm squared. So in the first case, this would evaluate to sigma 1 minus identity squared, right? And how much is that? Well, I subtract identity from this, right? So what do I get? I get the Frobenius norm of 0.5, 0, 0, minus 0.5, right? What did I do? I subtract identity from this, right? So this is -1, -1, and here are zeros. Now what about for the other one? That would be sigma 2 minus identity, Frobenius norm squared, right? So I take this guy and I subtract identity, and what do I get? I get 0.5, 0, 0, 0.5 Frobenius norm squared. And how does the Frobenius norm work? Well, it takes 0.5 squared plus minus 0.5 squared. Here I get 0.5 squared plus 0.5 squared. They are the same, right? So that's the problem. This energy does not see the difference between preserving volume and not preserving volume. Any questions on that? Anything unclear? My point is that this energy does not see the difference between the more volume preserving deformation and the deformation which has a lot of change in the volume of the material. And that's not good, because most real world materials, they tend to conserve their volume, right? Most materials in the real world behave like this. If you have a blob of material like this, and imagine you put a constraint here, you put like a steel bar here and another steel bar, and then you move them apart, and most materials do this, right? If I move them apart like this, they end up being like this, right? This was my material. If I stretch it by the ends, I get something like this, right? Like sort of rubber type of effect. This is called Poisson effect. And the material parameter that quantifies this effect is called Poisson ratio. Poisson effect or Poisson ratio. Now there are some special materials which have zero Poisson ratio, which means for zero Poisson ratio you get this type of deformation. It just does not collapse at all. So that means that the volume is not really conserved. Most materials behave like this. They have positive Poisson ratio, which is because the material wants to at least approximately conserve its volume. And now there are also some exotic materials which have negative Poisson ratio, and they buckle on expansion. It's pretty crazy. I have seen one material like this printed. One student at Princeton was showing me they 3D printed a material like this, and indeed, if you pull on it like this, it grows in the other direction. It's sort of funny. It's very rare. This is like extremely uncommon, but they exist nevertheless. But what we are interested in is mostly simulating real materials, which means we want to capture this type of behavior, which means we want to throw in some type of volume preservation into our material model. So this thing, as I demonstrated by this experiment, has absolutely no volume preservation, no incentive to preserve volume at all. This material, by the way, it would do exactly this if you just used it, right? So that's not super realistic. Some materials do behave like this. I think like cork or something like that behaves like this, but then there is only that much you can really stretch a cork before it breaks, right? So that's sort of good. If you want to be doing something more funny like rubber or something, or jello, then this is what you would want. So how can we incorporate this into our material and essentially get the full linear correlated elasticity and its different variations? How can we do that? So what we need to do is to introduce a volume preservation term, right? So how do I compute the volume of the deformed tetrahedron? So this is where I started. This is the rest pose, right? And my deformation function, like lowercase f, it maps it to some deformed tetrahedron, right? So when is the volume of the deformed tetrahedron the same as the volume of the rest pose tetrahedron? I think you could tell me that. That can be again characterized by the deformation gradient, right? Yeah, this is not exactly volume preserving, but it's more volume preserving than this. So volume is exactly preserved if and only if the determinant of f is exactly 1, right? If the determinant of f was exactly 0, then it means that it squishes it to the zero volume thing. If the determinant of f was negative, then it means we are doing the reflection. So we certainly don't want that. If we want volume preservation, that means that the determinant deformation gradient must be 1. So if the determinant of f is not 1, that means that we are violating the volume preservation by some amount, right? So the absolutely correct volume preservation term could be, oh, by the way, the determinant of f is of course the same as the determinant of sigma after I do the SVD, right? Because of course you know that f would be that u sigma vt, but because they are rotations, that's just determinant of sigma, right? So the volume preservation term I could use would be determinant of sigma minus 1 squared, right? And this is because I know that sigma is diagonal. This is equivalent to saying sigma 1, sigma 2, sigma 3 minus 1 squared, where sigma is sigma 1, sigma 2, sigma 3. We are all in 3D. So this would be a very nice volume preservation term, right? So what I could do, I could just take this term, multiply it by some coefficient, by some parameter, which says how much do I care about volume preservation, and add it to this term here. And I would have a very nice volume conserving material, right? Would not be conserving volume 100% because I don't enforce this as a hard constraint, as a strict equality. I only punish or penalize the deviation from volume preserving deformation. Make sense? Now the one slightly ugly thing is that this is now a degree 6 polynomial. It sort of complicates things a little bit. Like here I only had degree 2 polynomial expressed in sigmas, right? And here all of a sudden the degree grew a lot. Why is degree 6? Well, because here I multiplied 3 together, and here it goes again to the power of 2. So if you write out a bracket, you get sigma 1 squared, sigma 2 squared, sigma 3 squared is degree 6, which is like a lot of degree. So what is usually done in continuum mechanics is that we take this polynomial and we approximate it with degree 2 with a quadratic polynomial. Because the approximation is not going to be exact, I need to say where the approximation is most accurate, and I want to approximate it at the rest pose. That makes most sense, right? At sigma 1, sigma 2, sigma 3 being 1, right? That's my rest pose, right? In my rest pose, the sigma is identity, so all these sigma 1, sigma 2, and sigma 3 are 1s, right? So near the rest pose, I want the best precision. So again, what I'm doing here is I derived the exact volume preservation term. What I'm saying is that sort of ugly that's degree 6, I want to approximate by degree 2 polynomial, and I want to approximate it at this point. So one way to derive that would be to compute the derivatives of this. Because this already is a polynomial, there is, I think, a more elegant way to derive that, which I will show you right now. And this will lead us to linear correlated elasticity, Piola-Kirchhoff material, and linear elasticity. That's how we get the elasticity models that are typically used, not just in physics-based animation, but also quite a lot in continuum mechanics. Let's do this. So I have this thing. So I have a function, sigma 1, sigma 2, sigma 3, and it computes this, sigma 1 times sigma 2 times sigma 3 minus 1 squared, right? And I want to approximate this function at sigma 1, sigma 2, sigma 3 all being 1. So what I can do instead, I can do this substitution. I can define SIs, like new variables, which will be such that the sigma I is 1 plus SI. So approximating this at once is equivalent to approximating this new formula with SIs being zeros, right? So let me just rewrite this formula in terms of the SIs. Well, that's easy, right? All I need to do, so this would be equal to 1 plus S1, 1 plus S2, 1 plus S3 minus 1 squared, right? So I just took this substitution and I plugged it in for the sigma 1, sigma 2, and sigma 3. That's easy, right? So let me now expand the bracket. I mean, multiply this out. And what I will get is 1 plus S1 plus S2 plus S3 plus 2 S1 S2 plus 2 S1 S3 plus 2 S2 S3 plus S1 S2 S3, and there is still the minus 1, and that's still squared, right? So I just multiplied out these two products. Now what is this. So this 1 and the -1 here cancels, right? And this is still squared. So if I, again, factor it out, what I will get sigma 1 squared plus, S1 squared, S2 squared, S3 squared, plus S1, S2. I'll get plus S1, S2 plus S1, S3 plus S2, S3 plus bunch of other terms, and I will just call them higher order terms. Right? I'm just multiplying this whole thing by this whole thing again, which will generate a whole lot of higher order terms, which I fortunately don't have to care about. Why? Because I will only care about the quadratic part of this at S1, S2, S3 equal to 0, and at this point these guys will be all zeros. Or if you want to look at it as like taking a quadratic approximation, then I only need to look at the quadratic part. All these other terms, like for example, like S1 squared, S2, they would be higher order, higher degree, so I can discard them. Now the way I can write this, interestingly, is this is just S1 plus S2 plus S3 all squared, plus these higher order terms. I just will call them H0 because they don't really matter. And if I go back, undo this substitution, I can of course flip it the other way around. I can say that Si is sigma I minus 1. So what I will get? Well, I will get sigma 1 minus 1 plus sigma 2 minus 1 plus sigma 3 minus 1 squared plus higher order terms, which is just sigma 1 plus sigma 2 plus sigma 3 minus 3 squared plus these pesky higher order terms, right? And if I take just this, then this is essentially the second order Taylor expansion of this 6-degree polynomial at sigma 1, sigma 2, sigma 3 equal to 1, right? Because I made the substitution, if I compute the derivatives, if I take the second derivatives with respect to SIs, then only the second order terms, these guys, will survive, because the higher order terms, they will have at least one of the S's, which I substitute 0 with, so they really fall out. So this is the second order Taylor expansion. Because if you don't trust me, you can try to compute it the other way. You can directly differentiate this twice and get the Hessian of this mapping, and you should get the same thing. Now you need to make sure that you are taking at the right point, the point being 1, 1, 1, right? Sigma 1, sigma 2, sigma 3 being 1, 1, 1. Now, interesting thing, I can write this in a matrix form. So sigma 1 plus sigma 2 plus sigma 3 minus 3 squared. I can write this in a matrix form in a funny way. I can write this as a trace of sigma minus identity if I'm in 3 dimensions. This whole thing squared. So usually you just write trace squared of sigma minus identity. Why is that the same thing? Well, the sigma is sigma 1, sigma 2, sigma 3, right? That's my sigma. If I minus identity means minus this. So this is just sigma 1 minus 1, sigma 2 minus 1, sigma 3 minus 1, and trace just means sum the diagonal together. So this indeed is the same as here. Okay? So I can write this as a trace squared of sigma minus identity. And this is exactly what gives me the correlated linear elasticity. So if I define energy density function like this, here's a parameter mu, The first term is the term we discussed before. That's this term, sigma minus I. The second term is, usually it's like lambda half. I don't know why exactly. It's like, maybe, no, I don't know. Trace, and I use this term, sigma minus I. This doesn't matter, those are just parameters, so you can choose them whichever way you want. They are, however, relatively famous parameters because they have their own name. The mu and lambda are so-called Lamé coefficients. Or Lamé parameters. So in continuum mechanics, when you hear about Lamé parameters, those are exactly these guys. And what do they mean is that the mu parameter weights this term, which this term essentially is like the global deformation from the difference from the rest pose. But it doesn't care about volume preservation. And the second term is our second order approximation of volume preservation. So this is like the approximate volume preservation term. And this is like distance from rest pose. And this is the linear correlated elasticity model. Linear correlated elasticity. What the correlated means is that the rotation is correctly taken into account, that this material is correctly rotationally invariant. It's also isotropic. So I think this is one of the most popular materials in physics-based animation because it has the nice properties. It does penalize reflection. It works nicely, and all you need to compute and to compute it is the SPD. By the way, these Lamé coefficients are not the only parameters you can see. There are other type of parameters, essentially parameterizing the entire parameter space. What you might hear about is instead using Young's modulus and the Poisson ratio, which I already mentioned before. So the Young's modulus is typically denoted as K, and the Poisson ratio as mu, or I think it's mu. And there are a simple but nonlinear conversion formula. So the first Lamé parameter you get from these parameters like this, and the lambda you get like this. 1 plus mu, 1 minus g mu. And this K sort of means the overall material stiffness, and this is the Poisson ratio. So that means that the thing, if I have this blob of material, and if I stretch it like this, how much does it contract? That's the Poisson ratio. And there are all sorts of other parameters for linear elasticity, but ultimately it doesn't really matter which two you pick. Like if you are doing physics-based animation of some deformable solids, then you will probably be just tuning these by hand and seeing what does it mean for the material, how does it behave. Okay, any questions? So this is one of the nice material models, but sometimes people in graphics want faster simulation. So you sort of do some compromises. You sort of compromise this nice linear correlated elasticity model. By the way, this is by no means like the perfect model. Continuum mechanics has more accurate material models like the Nell-Huckian models, which I'm not going to cover in detail. You can read about them a little bit in Eftichias's notes. I think there is some part about Nell-Huckian elasticity. The problem is that it gets even more nonlinear, even worse than SVD. So the implementation is even trickier than that. So this would be the formula for the Nell-Huckian material. So my whole, so there are some logarithms of the determinant. The j is the determinant of the deformation gradient. So my whole point here, you don't have to worry about this. My whole point is that the correlated linear elasticity is not like the best thing you can do. There are about better material models out there. But for graphics, it's pretty good usually. It's so good that sometimes people employ simplified material models because they are computationally less expensive. The problem with linear correlated elasticity is that you need to get the sigma, which means that you have to run SVD. And you have to run SVD on every single tetrahedron, right? So it's a lot of SVDs you have to compute. So if you don't want to do all these SVDs, then there is an alternative material called Sand-Venon-Kirchhoff material, which has also been used in physics-based animation with some particular applications. And the idea is to simplify the linear correlated elasticity model. So instead of doing the SVD of the deformation gradient with Sand-Venon-Kirchhoff, must have been some German dude, I guess. So the idea is to use, instead of SVD, use the green strain. So the green strain is called E, so don't confuse it with the energy because that's a different thing. And it's computed like this. It's FTF minus identity. So I discussed this some the last time, right? Because this is a way you can get also rotation invariance, just like using SVD. But the downside was, what was the downside of this green strain tensor? Do you remember that? It's also reflection invariant, right? So it doesn't see reflections. If it happens that your elements reflect, then the green strain is blind to it, right? Because it just cancels out the reflections too. Nevertheless, if this is acceptable to you, then you can just use this cheaper material because here you don't have to do any SVDs. All you have to do here is FTF, right? That's just transposition and matrix multiplication. So that's a pretty easy thing to do. So then you can define the Sand-Venon-Kirchhoff material, which is defined like this. So you do the mu, that's the same mu as before, the first Lamé parameter. Here is my green strain. And here is trace squared of the green strain. So I guess the only reason I define the green strain here is so I don't have to write this twice. So if you compare it to the correlated linear elasticity, it's the same idea, right? There is mu times some total measure of global deformation, this time expressed using the green strain as opposed to using the sigma minus I. So here this is also the same thing, right? Sigma minus I, sigma minus I. Here is trace squared of it. Here is just the Frobenius norm of it. Here is lambda half. So it has the same pattern. So this is the Sand-Venon-Kirchhoff material. And the nice property of Sand-Venon-Kirchhoff is that this model is a quartic degree 4 polynomial of f of the deformation gradient. So it's sort of, if you will, it's sort of less nonlinear, or it's less menacing, less scary than the SVD. You don't have to compute any SVDs here. And the fact that this is just a degree 4 polynomial has been used in graphics, in particular by Jernej Barbic when he was doing the model reduction for Sand-Venon-Kirchhoff materials, because the fact that this is just a degree 4 polynomial means that after you do model reduction, you will also get just degree 4 polynomials, which you can take advantage of. I can discuss that in more detail later if you are interested in model reduction. So that's Sand-Venon-Kirchhoff material, also quite important material. But you might say, okay, quartic polynomial, that's still not quite ideal. Ideal would be just quadratic material model, right? Degree 2. Why is degree 2 energy nice? Quadratic energy nice? Because when we are computing forces, and I will cover that once we are done with the materials, how to compute forces. If you have a quadratic function, if you differentiate it, then your forces are linear, right? And it's very nice to have linear forces, because then you are just solving linear systems. You don't have to deal with all these non-linear things. So if you want a quadratic material, that's what's called linear elasticity. And that's probably the most basic material model, which does not even have a rotation invariance. And essentially the idea is to linearize the green strain, linearize E at, again, the undeformed configuration, at the deformation gradient being identity, right? So again, as I already started the course with, the physics-based animation is all about taking derivatives, and this linearization, that's no exception. That's essentially, again, just like another instance of computing derivatives. So what do we need to do here is to obtain linear elasticity out of Piola-Kirchhoff is to obtain a linear approximation of this expression at the undeformed configuration, at f equal identity. So that means we have to differentiate E. We have to compute the differential of E, which is a little bit funny, because if you think about it, what is E? E is a function that takes the deformation gradient. It's a function of f, right? That means E is a function that goes from 3 by 3, the space of all deformation gradients, and produces another 3 by 3 matrix, right? The green strain matrix. So it's really a function that takes a matrix and produces a different matrix, right? So the differential of E is just the same mapping, which is linear, which would technically be a R 3 by 3 by 3 by 3 tensor, right? So it means it's just something that consumes a matrix and gives us another matrix in a linear way. Now, I don't want to confuse you more than necessary with this tensor stuff. I was sort of trying to shield you away from this using the vectorization and matrix operations. But in this case, it turns out it's much easier to stay in the tensor notation to compute the differential of E. So we did not cover this when Tintin was doing the calculus introduction, but you can believe me that for the tensors, the same formulas apply for the differentials. Because after all, it's again all just taking linearizations of some function, and the fact that it's a matrix function does not change anything. So standard calculus rules still apply. So for example, the differential of E is what you would expect. It's 1/2 of differential f, the whole thing transposed, times f, plus f transpose times the differential of f. The identity disappeared in differentiation. So what this means is a local linear approximation of E is related to local linear approximation of f using this formula. And if we plug in, if we say that we are taking the linear approximation and f equals identity, then the differential of f becomes just f minus I, essentially. So if we do this, if we do the differential of E, double contraction with f minus identity at identity, then we get this. So what I do, for the differential of f, I plug there f minus identity, the whole thing transposed, and for f, I will just give it identity, because that's where I am computing the derivative. So here is identity transpose, well, just identity, right, times the differential, which is differential of f, which is just f minus I, the linear part of the transformation. So after all this funny mumbo jumbo, all I get is f transpose minus identity plus f minus identity, right? Because I have 1/2 here, this is just 1/2 of f transpose plus f minus identity. And this is exactly what is called the small strain tensor, usually denoted like lowercase epsilon, 1/2 of f plus f transpose minus identity. This is called a small strain tensor. It's, I mean, this is stupid to call it tensor because it's just a matrix. So it's not like a tensor like this guy. This is just a matrix, but like in continuum mechanics, people like to call tensors everything, even matrices. So small strain tensor. It's of course just a 3x3 matrix, right? It must be F is a matrix, I is a matrix, so it's nothing that special. By the way, what does it mean, the F plus F transpose? Just in terms of linear algebra. It's a very, huh? Outer? No, that means this is the symmetric part of the matrix.
Oh,
right?
Okay, I saw it.
You know that? Yeah, I know you meant it right. Every matrix you can decompose into a symmetric part and anti-symmetric part. This is the symmetric part, this is the anti-symmetric part. So this is exactly the symmetric part of the deformation gradient, which is essentially a poor means of doing rotation invariance. It's sort of like linearized rotation invariance, if you will. So this small strain tensor works, but only for small rotations. If you have like larger rotations, like 90 degrees and more, then this will start showing up lots of errors. So, and then what is the formula for linear elasticity? Maybe you could tell me that now. It's again the same pattern. It's mu times the small strain tensor Frobenius norm squared plus half of lambda times the trace squared of the small strain tensor. And the beautiful thing about it that this is now quadratic in f. Why is it quadratic? Well, this is linear on f, right? And this is a quadratic function of the deformation gradient or of the small strain tensor. It's also quadratic, so altogether it's just a quadratic function. So that means that the derivatives of that will be linear, and the Hessian of that will be constant, which is very nice. The downside is that this only works well for relatively small rotations. If you have larger rotations, then this small strain tensor will essentially confuse them for deformations, for stretching of the material, which means that if you will rotate your material and use this material model, then it will prefer to deform rather than to rotate, which is not great. So there is always trade-offs. There is no single perfect model that would be like a clear winner. If you want faster computations, then you go for linear elasticity, but then you lose rotation invariance. If you want some beautiful rotation invariance properties, then you use the linear correlated elasticity, but you have to pay for it by computing the SVDs. So that's why we have all these material models, because each of them is useful in slightly different situations. Okay? Now the last thing I wanted to show you is how to compute the forces, how to be actually able to use these materials in an actual simulator. So now we have all these materials, and how do you actually use them? So what does it mean to use them? Well, it means that you need to compute forces due to these materials, right? So each of these tetrahedra I can basically consider as a generalized type of spring that acts on 4 vertices, right? And the blob of material contained in this tetrahedron will exert some elastic force on each of the 4 vertices. So how do we compute them exactly? So we can just do this for one tetrahedron, right? Because then if we have like another tetrahedron next to it, like there's another guy here, then like of course like if I take this vertex which is shared by T1, tetrahedron 1 and tetrahedron 2, then obviously the force, the total force on this of this node will be simply the sum of the forces going from tetrahedron 1 and from tetrahedron 2, right? So forces you just trivially sum together. So we need to only figure out what are the forces acting on a vertex K due to one single tetrahedron. So let's assume I have just one tetrahedron with vertices x1, x2, x3, and x4. They are all three-dimensional vectors. And let's say that I have some energy which is defined using any of the material models I discussed. So that's my psi. And here is the deformation gradient, which depends on x1, x2, x3, and x4. Right? And what we want to do is compute forces. So forces will be F1, F2, F3, and F4. So those are the forces acting on all these vertices. And they are also three-dimensional vectors, right? So as I said, if I have just forget about the second one, let's just look at one tetrahedron. And due to deformations of the material in this tetrahedron, there will be some forces acting on each of the vertices. And for a chosen material model, pick your favorite one, whatever, it works for all of them equally well. We need to compute the forces. So how do we compute forces? So let's say force number K, where K is from 1, 2, 3, 4. So how is the force computed? You tell me that real quick because I want to finish it today. It's the negative derivative of my energy with respect to particle xk, right? That's always the same rule. This is the elastic energy. If I want to go to force, I differentiate by the vertex I'm looking at, and that gives me the direction of steepest ascent. So I want to go steepest descent, so that gives me the force. That's why the minus is here. Now the forces are 3D vectors. So force K consists of three numbers. I need to look at the coordinates, unfortunately, as much as I like to avoid writing individual coordinates here, I will have to. So the Fk1 is the x coordinate of the force, Fk2 is the y coordinate of the force, Fk3 is the z coordinate of the force. Okay. So how to compute these individual forces? Well, then I guess it's sort of obvious to say that the jth coordinate of the force, just to get the notation nailed, is the derivative of my deformation energy with respect to x, k, jth coordinate. J goes from 1, 2 to 3 if you are in 3D. Okay. So now what is the formula for this? We are going to use the chain rule here quite obviously, because the elastic energy depends on psi, which in turn depends on F, and the F depends on the axis, right? So the chain rule dictates that this is going to be the Jacobian of, or is it Jacobian? Psi by, let's just say differential, that's more neutral, by F, double contraction F by x, k, j. Oh, by the way, do you know what is the double contraction? Am I not okay, you should have asked that before. That's actually something super simple. It just sounds fancy, but it's like very simple. If I have two matrices A and B, let's just say that they are n by n. This is also n by n. So the double contraction is as simple as that. It's Aij times Bij going over all ij. So just like put the matrices together, do the products of the things and sum everything together. So if the matrix A has elements Aij, the matrix B has elements Bij, I just put all the corresponding elements together, multiply them, and sum everything. So the psi was a scalar function of the matrix argument, right? So after I differentiate, I will get a 3 by 3 matrix. the f was on the contrary, f is a matrix, and I'm differentiating with respect to a scalar, so this is also a 3 by 3 matrix, right? Sort of trying to write it in matrices because they make more sense than these funny tensors. Now this psi differentiated by f, this has a fairly important quantity which is denoted as pf. Again, it's just a 3 by 3 matrix, and this is called the Piola, some dude, stress tensor. Or if you want to be really rigorous, you would call it the first Piola-Kirchhoff stress tensor. I'm not gonna write, that's too many words. This would be the first Piola-Kirchhoff stress tensor. And what it really means is just differentiating this deformation energy psi with respect to the deformation gradient. That basically tells me if the deformation gradient is changing, how the elastic energy is changing. Okay? And I can compute this relatively easily for all the materials we have discussed. So I'll just assume we have that. And the remaining piece is what about differentiating the deformation gradient? It's all about differentiation. Can't help it, that's what it is. So before I said that this is the SDM inverse. We had defined these matrices before. Let me just remind you, the ds was this, x1 minus x4. Those are the vertices of my tetrahedron. x2 minus x4 and x3 minus x4. The dm matrix was exactly the same thing in the rest pose. So this dm inverse is something I typically pre-compute. In the simulation, this never changes, so this doesn't really bother me too much. And if I want to differentiate this, let's say by x1, 1, so the x coordinates of x1, what would that be? I'm differentiating this, so this is constant here, doesn't bother me. I'm differentiating this with respect to the first coordinate of x1. How much is it? You still remember your calculus thing? Maybe I should have given you more differentiation works. Well, the x1 is only here, right? And this is the x, y, and z coordinates here. So what I will get here is just this. Like this, and the dm inverse, that's constant. So that's really easy thing to differentiate, right? So the other way I can write this is as E1 transpose dm inverse, where E1 means the standard basis vector, 1, 0, 0, okay? It turns out that in general, if I want to differentiate the f with respect to x jth coordinate of xk, what I will get is simply Ej ek transpose dm inverse, where of course the j goes from 1 to 3 and k goes also from 1 to 3. That's simple if you think about it for a second, right? If I have the second coordinate, I get the 1 here, and this k tells me which column I am selecting. If you think about it for a second, it absolutely makes sense. The only tricky thing here is differentiating with respect to x4. The x4 is different from x1, x2, and x3, right? x4 was the vertex which I sort of chose as the pivot, so that the edges are expressed with respect to x4. So if I'm differentiating with x4, for example, the first coordinate, what do I get? Now you have to tell me that. So I'm differentiating with respect to x4, this formula. So it will be -1, -1, -1, and zeros everywhere else times dm inverse, right? So the way I can write this is as E1 U and dm inverse. Oh, U transpose dm inverse. Where what is U? I will say that U is like a vector of all ones, like a unit thing. Oh, and minus here, because there is a minus. And we are almost there. Because all I need to do now is what do I need to do now? To go back to the chain rule here, so let me copy it here. So differential of E with respect to x, k, jth coordinate is the Piola-Kirchhoff stress tensor, the P thing, times Ej ek transpose dm inverse. So this is for vertices x1, x2, or x3. So for k, 1, 2, 3, this is true. So by the way, this A double contraction with B, I can also write it, if you think about it for a second, it's obvious, as A, B, trace of AB transpose. So that's what I will use here. So I'll write this as trace of P, and then I will transpose the whole thing. So dm inverse transpose, ek, ej transposed. Okay. In a trace, we have done this before. You can switch these things around. So I can just flip the ejt from here. I can just put it here. P dm inverse transpose ek. Now this is a scalar, so this trace is here saying nothing, right? So this is just ej, I can get rid of the trace, P dm inverse transpose ek. And then what is this? This is sort of cool. Remember, what was the ej and ek? Those are just standard basis vectors, right? They are like all zeros except for 1, 1 in the jth coordinate. So what this means is nothing but taking matrix P dm inverse transpose and taking element j and k. So this is a 3 by 3 matrix, right? K goes from 1 to 3, j goes from 1 to 3. And this means nothing but computing matrix P dm inverse transpose and taking the jth and kth element. So that means that if all I need to do is really compute this matrix, P dm inverse transpose, and if I negate it, this matrix immediately contains the forces I needed to compute, F1, F2, F3. So this is essentially like a 3 by 3 matrix of the forces. In the first column is the force 1, in the second column is the force 2, in the third column is the force 3. The only remaining bit here is you need to compute the first Piola-Kirchhoff stress tensor, which you can either directly differentiate or you can look at FTQS's course notes where the first Piola-Kirchhoff stress tensor is derived for all these materials we discussed here. Now why did I take the minus? That's because the force is minus the derivative of the energy. The one remaining bit here is what about K4? What about the last guy, right? That's the X4. So there the formula is a little bit different. Remember that we had that the F by X, the first coordinate was like this, right? So it was -1, -1, -1, 0, 0, 0, 0, 0, 0, which I can write as minus E1 U transpose. So in general, if I want to do that, it will be X. I guess I can give you a homework here to derive this EJU transpose. That just means the same is true for every coordinate. And that means that if I will differentiate the E like here, but I will go now for the fourth particle, X4, all of the coordinates. Then what I will get, you can do this for your homework. It's essentially the same thing here, except that you use this instead. You will get minus EJ transpose P dm inverse transpose U. And all that means, again, I'm skipping, you can fill in the blanks. by yourself. That means that the f4, which is of course the negative derivative of this, is simply minus f1 minus f2 minus f3. Which you could tell me, well, that's obvious, because if it's just due to elastic energy on a tetrahedron, then obviously the tetrahedron, due to its own elasticity, cannot start moving itself. It needs to conserve the linear momentum. So all these forces, F1 plus F2 plus F3 plus F4, must sum to 0, which is exactly what this equation says, right? So that's another reason why F4 must be minus F1 minus F2 minus F3, because the momentum on my blob of elastic material needs to be conserved. This is, by the way, exactly the same as we have seen on springs, right? The spring was essentially just like a poor man's version of this. The spring had just 2 particles as opposed to 4 as we have on a tetrahedron, right? And on a spring, we also had that F1 plus F2 must be 0, right? The spring also cannot start moving by itself. So all this really is just a refined version of a spring, if you will. And if you will be implementing that, you will find useful the pseudocode in the tutorial. I'll show you this. It's a very nice pseudocode. It essentially summarizes all these calculations I have just derived. It's this thing here. This algorithm 1. It sort of splits the pre-computation. So here I'm computing the DM matrix. That's this DM matrix here. Here I pre-compute its inverse. I pre-compute the volume, and I store this. This is like a pre-computation. And then when I'm computing the forces, I compute the deformation gradients. I mean, the deformation gradient is ds times the pre-computed matrix here. Here I grab my Piola-Kirchhoff stress tensor, depending on whatever material did I decide to use. And now you see there is like a palette of materials you can use in your simulations. Here I weight it. Here I weighted by the volume. Yeah, I left out the volume from these equations. You could imagine that they are all multiplied by the volume of the element, as we discussed before. Here is the multiplication by the dm inverse transpose. I guess here it's called bm transpose, so it's like a little bit deviated from the notation. And in this H matrix, that's exactly what I computed here. That's this matrix where in the columns you can directly read off the forces F1, F2, F3. And the last force you will get as summing them together and negating the whole thing. So that's how it works. And now you can go and implement explicit Euler integration. If you want to do implicit integration, that's what is the rest of the notes about. Then you have to differentiate this thing again. So I'll just spare you the pain of differentiating that again. And actually a good way to spare you the pain is to do the projective dynamics paper, which I talked about the last time, where you don't really have to, where you can do implicit integration without differentiating this thing one more time. So maybe if you are interested, I might cover that later because some people are working on that and it's sort of nicely fit. Okay, so we are right on time. Any questions? Everybody's sufficiently confused. Well, that's why you have it on video. I think it should make sense if you think about it for a second. Or two.